Good morning, everyone. We're going to continue along here in chapter 3 today. Try to wrap the chapter up. We might get a quick introduction in chapter 4 as well, but we'll be continuing into chapter 4 Wednesday through next week. Our next exam is over chapters 3 and 4. I think midterm 2 is usually one of our lower averaging exams. It doesn't have to be the lower averaging exam, but I think it's just kind of maybe the first exam where we kind of kick up the pace a little bit. The challenge level gets a little bit harder from chapters 1 and 2. So and hopefully scores get out soon for midterm 1. But if your score is really good on midterm 1, just don't think that the class is super duper easy. We got to keep working, keep reading, keep studying, keep working practice problems, coming to class obviously, and then hopefully the material makes sense and we can continue to be successful in the course. I've seen scores go from midterm 1 from like a perfect score into like the 40 to 50% range. I've also seen students that score in the low range on midterm 1 and rebound for midterm 2 too. So a lot of things can happen from midterm to midterm, but just keep working, keep trying. When you're stuck on things, if they don't make sense, dig deeper into them, seek help out from me, AI, TAs, etc. But with that, we'll head back into chapter 3. So this slide here is just meaning to kind of introduce some of the concepts of like limiting versus excess reactants, which we've talked a little bit about already. But let's talk within the with respect to a particular chemical reaction, and let's talk about sodium. Sodium's a solid at room temperature. Let's talk about the reaction with chlorine. Chlorine's a gas at room temperature. We can predict the product of this reaction. This is one of the introductory reactions we talked about. We talked about combination reactions, which this is, where we can combine a metal and a non-metal to make the ionic compound. So we should be able to predict that the ionic compound would be the common ion of sodium, which is sodium plus, and then the common ion of chlorine, which is Cl minus. So we should be making NaCl, and the physical states really aren't the point of this example, but sodium chloride is a solid at room temperature. If you know that, that's helpful. If not, it's not a big deal. Chlorine happens to be a gas at room temperature. But if we wanted to balance this reaction, we do 2's in front of the NaCl's for 2 chlorines, and then that gives us 2 sodiums, so we need a 2 in front of sodium. But I just want to have a chemical reaction to kind of think a little bit about limiting versus excess reactants and what the coefficients mean, what the subscripts mean. So of course the subscript just means 2 chlorines are bonded together. So we have 2 chlorines bonded together, that's what the 2 means. And then the 2 sodiums, we can picture either like 2 sodium atoms that are separated. It's a little bit tricky to think of sodium chloride because it's really a solid network of atoms that are all kind of metallically bonded together. But somehow we have 2 sodium atoms that aren't necessarily linked per se, at least within the 2 out front just means we have 2 equivalents of sodium. If we're thinking on the atomic level, I'm probably thinking like this. If we're thinking on the mole level, I could have 2 moles of sodium, which is a lot of sodium atoms, right? It's going to be 2 times Avogadro's number. We're going to have an Avogadro's number of Cl2 molecules, but the ratio of 2 parts sodium to 1 part chlorine. Then we get 2 parts NaCl to form. Now, the coefficients in front, the 2-to-1 ratio of sodium to chlorine, doesn't mean that I have to mix that ratio of sodium and chlorine together. I can mix together whatever proportions of sodium and chlorine I wish. I could have a little bit of sodium, a whole lot of chlorine, and then I'm just going to have a whole lot of chlorine left over after the reaction finishes as my excess reactant. And then likewise, I can have a whole lot of sodium, tiny bit of chlorine, in which case only the chlorine will react, and I'll be left with a lot of sodium left after the reaction completes. So I can have one of the reactants be in excess, where I just have too much, and it just remains after the reaction completes. And then the limiting reactant is the one that's consumed. And just meaning it drops to 0, or its amount after the reaction completes is 0. And so then we can then get into a discussion of theoretical versus actual yields, because sometimes reactions have byproducts, or they have, maybe we lose material in the laboratory, maybe we make a mistake in the lab and we don't get the yield we expect. And so let's say we take that proper 2-to-1 ratio. Let's say we actually take 2 moles of sodium, 1 mole of chlorine, and we should get 2 moles of sodium chloride out from that reaction. And let's say we only get 1.8 moles. If I only get 1.8 moles, if I do that experiment and I say, hey, I weighed out my sample, I just don't have the mass I expected to find, then I just have a lower percent yield. So my percent yield is just simply the actual yield that I get divided by sometimes what we call the theoretical yield. Think of the theoretical yield being the maximum yield. And it's the maximum yield you expect from the limiting reactant. So from which reactant was the limiting reactant, that's the yield you calculate off of that reactant being completely consumed. And then times 100% to put that into a percentage. So example, you get 1.8 moles, you expected 2.0 moles, then the percent yield in that case would be, what's that, 90%? Probably 90%. Like I said, sometimes I double check even basic math just to make sure my head isn't lying to me. Yep, that's 90%. So the calculation of yield, very simple. It's just what yield did we get versus what did we expect, and the expected yield or the theoretical yield or the maximum yield is yield we would calculate from whichever reactant was completely consumed. And the generic example we just made up of 2 moles of sodium, 1 mole of chlorine, either one of those, like both of those are the limiting reactant. They're both hitting 0. Neither one were in excess. And so the theoretical yield, again, this is the one that comes from our stoichiometry, from the limiting reactant. And then the actual yield is what we actually get. So that's the yield we actually obtain in the reaction. All right, so let's look at a couple examples that we'll put into practice, calculating, things or determining limiting versus excess reactant and determining things like. Okay, so let's take a look at this example here. So let's say we have 15 grams of N2, 2.5 grams of H2, fully react together according to the reaction below, which we looked at this reaction last time too. It was N2 plus 3H2 goes to 2NH3. Which reactant is the limiting reactant and how much product forms? So kind of a two-part question is like which reactant is the limiting versus which one's the excess reactant. We have to determine that problem first, and then we also have to figure out how much of the product NH3 forms in grams during this reaction. Now, our options that we have are making a picture, probably too big a quantities to make a picture, so I'm probably not going to go to a particle diagram on this one. I could set up a BCA chart on this one, the before, change, after. It's not my go-to. It's not necessarily the one that I would think of setting up because I don't have mole quantities. If I had to set up a BCA chart, the B has to be the moles of nitrogen, the moles of hydrogen, and I could calculate those. I could write it out, but in terms of problem solving, I'm probably just thinking dimensional analysis. I'm probably thinking, can I just try to determine the number of grams of NH3 that would form if we consumed all of the first reactant? Let's consume all of the nitrogen. And the idea would be if we lose all that nitrogen, go to 0, then we have to have at least enough hydrogen to react with it to produce the product. So we're assuming that as long as there's enough hydrogen around for it to react with, then it should be able to convert for every 1 mole of N2 into 2 moles of NH3. And that, again, assumes that we have that 3 moles of H2 around for it to react with. Okay, so I'm going to consume all the nitrogen. I got to convert it to moles, so let's do that here within the step. So nitrogen's 14.01, so N2 would be 28.02 grams per mole of N2. And again, this is just from the periodic table. And then the next step would be our conversion from the coefficients in the reaction. So I have for every 1 mole of N2, that when it reacts and is lost, we form 2 moles of NH3. So 1 part we lose, 2 parts we gain. And assuming again that we have those 3 parts of H2 for it to react with. Since we want the mass of NH3, we'll just go the moles of NH3 into the molar mass. So 1.008 for hydrogen times 3, plus 14.01 for nitrogen, 17.03. So I'll just calculate this. Now the first part, the 0.535 moles of N2, I could write that down, make a BCA chart. I might ask after the problem is done for us to maybe calculate a BCA chart. So I'm just going to write this here to 3 sig figs, just because it might be helpful later. So I'm just going to calculate the first 15 divided by 28.02 and write that down. I'm going to use this number a little bit later just to do a quick BCA chart when we're done, just for a second approach here. But I'm going to take that and continue on here times 2 and then times 17.03. So that gives me 18.2 grams of the product should form or would form if we consume 15 grams of nitrogen with the required amount of hydrogen to react with it. Now, can anybody see already that this actually can't form, that this would be an impossible amount of yield to get in this reaction? Because I have 15 grams of nitrogen, 2.5 grams of hydrogen. That's 17.5 total grams. My product mass is over 17.5 grams. So we can already predict that probably this nitrogen is not going to be the limiting reactant. Like, we just clearly aren't going to have enough hydrogen, but we can show for sure and then calculate the proper amount of ammonia that can form, because anytime we solve a problem like this anyways, we kind of have to run through the math a second time with the other reactant to make sure that it makes less product. So if you remember, or if you've ever seen this problem before, we talked about it a little bit on Friday, that you can try to make the yield of your product, make all the product you can make from the one reactant, and then see how much product you get from the other reactant fully reacting, and whichever quantity is less is the most you can get of your product, because you've consumed all the reactant, the first reactant, when you get the lesser amount of product. So let's just run through this again and talk about why it works and the thought process again once we see the answer. So again, we're calculating the grams of ammonia, consuming all the nitrogen, or excuse me, all the hydrogen, which is 2.016 grams per mole of hydrogen. So remember, it's grams of H2. That's why we're using the molar mass of H2 for two hydrogens together. Now our coefficients here are for every 3 moles of hydrogen that react, provided we have the proper amount of nitrogen to react with it, then we will form 2 moles of NH3. Molar mass of NH3 is the same mass, 17.03 grams. Again, I'm going to stop and calculate and write it down after the 2.5 divided by 2.016. That's 1.24 moles. But we'll talk about that later. So I just wanted to jot it down so I don't have to calculate it again later. But so I'm going to keep going. Times 2, divide by 3, times 17.03. And I get 14.1. So I hit 14.1 grams of ammonia. And at that point, my hydrogen's dropped to 0. It's been consumed. So my hydrogen's going away. And I'm gaining my product in this reaction here. So I'm losing the H2 as I'm gaining the NH3. So I've gained this much mass, and now I've hit 0 on my H2. I'm all out of hydrogen. So I don't have enough hydrogen to go from 14.1 grams up to 18.2 grams. If I want to get this yield here, I need to add more hydrogen to the mix. So I need to have more hydrogen to react with the N2. So in other words, nitrogen is going to be left over. This is the excess reactant. And then the hydrogen, of course, here we see is our limiting reactant. It's one that limits the amount of product formation. Okay, so how much product forms? 14.1 grams. We don't get the 18.2. And then we identify the limiting reactant in this approach as being the hydrogen. Okay, now could we do a BCA chart? Could we have done this instead? Can it be a second way or just like a backup or just an alternate way? I think if anything you get from the BCA chart is just maybe the thought of what's going on in the reaction. If you're kind of getting lost on things reacting, things forming, let's quickly try to think of a BCA chart. I'm going to rewrite the reaction up here, write a little bit smaller to try to fit it in the screen. Now my before, the key for the before, what is this? This is the, people who watch this video, what is going on? My screen keeps cutting out. It's like I can't win with either going online wireless or hardwired. Okay, so let's think of our before change after is what BCA stands for. And so the before, the key detail here is I want to write the moles in here. If I write the grams in, it doesn't really help. If I write the 15.0 to 2.5 and I start writing minus x's in here, I need the coefficients to be I need the quantities to be in moles or molecules. So when I'm filling into the chart, moles or molecules, because we have to go reacting units. Now I can't write either. Moles or molecules into a BCA chart, not mass. And so I would have had to stop and calculate it like we did, the 0.535 moles of N2 and then the 1.24 moles of H2. And then my minus X and my minus 3X, the minuses are because they're reactants that are being lost. And then the coefficient in front of X is just the coefficient in front of the N2 being a 1, so it's minus 1X, and then minus a 3 in front of H2 for the other. From this point forward, this is a re-record from today. We had an issue with the screen today in class, and I had to stop and change something, and then I forgot to hit play for this slide and the next slide. So from this point forward, might be a little disconnected from where the video had just previously cut off from. But what we were trying to set up here is our BCA chart. So we had our 4 moles for N2, H2 written in. There's no product yet initially present. Then the minus X, minus 3X, and then plus 2X for the ammonia coming off of their coefficient. So we're losing reactants, so the minus, and then 1 for, so minus 1X for N2, minus 3 because of the 3 in front of H2 for H2, and plus 2 because we're gaining the product in those 2 parts. So for every 1 N2 we lose 3 H2s, and we gain 2 NH3s is the idea. And so then, do we know any of this information? Or let's write out, yeah, so which of these 2 here go to 0? Is it the H2 that goes to 0 or the N2 that goes to 0? Now, we already knew from the math below that it's probably the H2, or should be the H2. But if we did make it mistakenly the N2, if we imagine making this as 0, then X would be 0.535. 1.24 minus 3 times 0.535 goes negative. So, of course, we can't go 0 for N2. And if we go 0 over here for H2, then we can solve for X. So 1.24 minus 3 times X would be equal to 0, so we can solve for X. So I can subtract 1.24 from both sides. So then that would be minus 1.24 is equal to 3X. And so then X is equal to minus 3X. It would be equal to minus 1.24, divide both sides by minus 3. And then that will give us X is equal to 0.413. And so then we can solve for a few things. We can see that we'd have 2 times X, so that's going to be 0.826 moles of our product. And then we're going to see that 0.535 minus 0.413 is 0.122 moles. And then you can convert with the molar mass, 17.03 grams per mole of ammonia, so that's results in being 14.1 grams. You can even work out that you have 0.122 moles of the remaining N2 and calculate specifically how much of the excess reactant remains. So the after is the remaining, and then the X is the consumed, and then B is the initial amount. Okay, so we can set up BCA charts. They kind of help us understand what's going on, even if they're not always the way on a test. That, maybe they're not the go-to method on a test to write out the math for a problem, but they're a good thought problem. They help us understand what we're writing in our dimensional analysis steps, hopefully. All right, so looking at this question here, same question. So 15 grams of N2, 2.5 grams of H2 react according to the same reaction. But if we only get 12.2 grams of product, what's the percent yield of the reaction? So percent yield is our actual yield divided by your theoretical yield times 100%. And then that should be, so clearly 12.2 is what we actually got in this reaction. Then what do we write in here for our theoretical yield? Now, if we go back to the previous slide, we had 2 numbers for the mass of ammonia that could be formed. It's the lesser. We want to choose the theoretical yield off the limiting reactant being consumed, stoichiometry, and so that was 14.1 grams. So for the given quantities in the reaction, the yield of ammonia is the one that's linked to the limiting reactants being completely consumed, And so then this works out to be 86.5% yield. And so a true yield of a molecule in a reaction should never go beyond 100%. Maybe a lab mistake could lead us to thinking the yield goes above 100%, but the true yield of a substance in a reaction cannot go above 100% yield, otherwise we'd be creating matter. Okay, so again, same question. Now this one's asking something again slightly different. Which reactant is limiting which one, and how much of the excess reactant remains after this reaction completes? So for this question here, how much of the excess reactant remains? We could go back to that BCA chart. If you recall, we had the 0.535 minus the 0.413 equals, and there's a number there that we could calculate the number of moles, convert it to grams, and we could solve it with that BCA chart approach that we previously used. Let's think of a different way. So let's go through a dimensional analysis sequence where we can figure out the excess reactant that remains by using dimensional analysis, as perhaps maybe this is the only question we saw on this topic, and we're doing it again from scratch. What I might think here is, well, how do I apply dimensional analysis to the question of how much of the excess reactant remains? What I think I would try to figure out is, well, how much of the excess reactant had reacted with the limiting reactant, and try to solve that question by dimensional analysis. So I might address this question here. Now, this question could have two starting points too. If we didn't know the limiting reactant already, then we would just calculate how much N2 is required to react with the given H2, and then we would calculate how much H2 is required to react with the given N2. And we can run through the problem both ways. And this problem here, if you're lucky and you choose the limiting reactant right off the bat, should solve itself. It should prove to you that reactant's limiting, and I'll explain why that is once we get the number here for N2. So we start with the H2 that's given, because we already know the limiting reactant. So we are starting with what we know to be the limiting reactant. Same conversion. We need to use our mole ratios in the reactions. We got to convert to moles. Almost every problem with stoichiometry is going to have a gram to mole conversion, or at least you have to have moles or molecules somewhere along the way. So for every 3 moles of H2, we need 1 mole of N2 to react with it. And for every 1 mole of N2, since the quantity is given in grams here, we want to convert that to grams, so that's 28.02 grams. So this problem here will tell us how much of the N2 reacts with that given H2. So I get 11.58, call it 11.6 grams. Now, does 11.6 grams of N2 remain? No, that's the amount of N2 that reacts and is destroyed by the reaction with the H2. So that's the amount of N2 that we lose. So the remaining N2 would be equal to the initial amount given, 15.0 grams. And then, of course, minus the 11.6 grams that reacted. So that should leave 3.4 grams. So 3.4 grams of the N2 should remain after the reaction completes. Now, again, if you remember this from the previous page, or you had just solved the BCA chart, then we could have calculated it from here too. So you can go back to the BCA chart or have solved the problem that way from the start, and then the answer is right there, 0.122 times 28.02, 3.4 grams. So we can go back to the BCA chart or have solved the problem that way and gotten the answer as well. But I think the BCA chart shows us the very clear, you have the initial amount, you have the change, you have the after in moles, and then here with the dimensional analysis, we're just working out that problem with the masses once we calculate those and can take the difference of the masses. Stoichiometry problems always have numbers. Like that's the one thing in a stoichiometry problem. You can always, go from one to the other, take this times 2, divide by 3, whatever. You get numbers that look sensible. The question is, what do they mean? How did you get to them? Did you divide by 2 and multiply by 3, or are you supposed to do it the other way around? Writing units out is very helpful, so you can track and cancel. And again, I'm not always canceling these out on my paper, but you can see that the idea is that those units should be canceling. If they're not, and you're not seeing that they're canceling because we're not writing the units in, we're going to get a lot of these coefficients backwards. We're going to divide by things we should multiply by, etc. Okay, so hopefully we have a few different ways of solving problems, a few different ways of thinking through problems and understand stoichiometry better. We have plenty more examples we can give, like this one here. There's going to be a few more examples within Chapter 4 notes going back to some stoichiometry problems because it's an important topic. We need to know it. It's one of the topics that you'll see a bunch throughout later chapters in this class and into your other chemistry classes. So let's take a look at this problem here. So you have 12 grams of H2 and an unknown amount of oxygen. And when the reaction takes place, we form 76 grams of water forms by the given reaction of 2H2 plus O2 goes to 2 waters. How much H2 is remaining and how much O2 had reacted with it if the reaction goes to that 100% yield? You'll see a lot of problems say, assuming the reaction completes or goes to 100% yield, that just means that there's no byproducts to worry about, that you're just getting all the yields as you expect from the stoichiometry in the reaction. So how might we set this problem up? Well, the two basic approaches, I think, would be either a BCA chart, and that's fair. There's nothing wrong with kind of trying to think here of what's present initially. Only thing we might do is we might convert the grams to moles. Can I divide that by 2.016 without showing it, like the grams to mole? Maybe I should show it. Just if I want to go to moles of hydrogen, I just go 2.016 grams per mole of H2. So I'm just using the molar mass of that substance. Because if I go into my BCA chart, I just want to put moles into it, not grams. So I'd have 5.95 moles. I don't know how much O2 I have. That's one of the unknowns in the problem, is trying to figure out how much O2 had reacted. Initially, no water, so we don't initially have any water. And then my minus 2x minus x plus 2x are just coming from the coefficients, and then noting the reactants being lost, the products being gained. Oops, that's not actually x. It would be question mark minus x. Like, so the initial amount minus however much we lost for the O2. So that's a question mark. Now, what can we solve in the chart? Like, how might I find x from the BCA chart approach? Do we know how much water forms in the reaction? We do. It says 76 grams. Now, moles go into the chart, so I just have to convert this to moles. So I use the molar mass of H2O, so that'd be 76 divided by 18.02. That's 4.22. I'm going to keep an extra sig fig, call it 4.218 moles. That's what 2x is equal to. 2x is equal to that number of moles. That's how many moles I have of water after the reaction completes. So I can solve for x. So how much oxygen reacted? X. X is the amount of oxygen that was lost. So that's the amount of oxygen that reacted. So the amount of oxygen that reacts here, 2.109 moles. What's the molar mass of O2? Periodic table, 16 times 2. So that's 32.00 grams per mole of O2. So that's 67.5 grams of O2 that were consumed during this reaction. We don't know initially how much there was, but we do know that that's how much the O2 had reacted. So the answer is probably A, but just to make sure that it's A, let's calculate the mass of hydrogen that remains. So that's right over here, the 5.95 minus 2x. Again, I have my x, so I just have to take 5.95. Oops. That's a minus sign. So 5.95 minus 2 times 2.109 is 1.73 moles. Times 2.016 grams per mole, 3.49 grams. So that leads us to answer A. You know, the tricky part on the BCA chart is, one, knowing you can set it up and thinking that it might be a way to solve the problem. But the other tricky part, I think, is just seeing that we can find out what X is by the information that's given and then just apply what X is to solving for the amount of O2 that reacted and the amount of H2 that remained. I think this is a pretty tricky problem. This might have been a better problem like a couple of days from now once it's kind of settled in, but we do have more problems we can keep showing. I think there's one more for today for stoichiometry that we'll look at today, and then we'll kind of try to move away from these problems, let it percolate a little bit, do some more problems at home, then come back to some review problems later. But we could have solved this by dimensional analysis. How many of you guys were thinking the BCA chart seemed like a bad idea and wanted to use dimensional analysis? Was anybody thinking that? Some of you guys may be like, this is kind of boring and annoying to have multiple ways of solving every problem we see. But we could have been thinking, well, why not just use dimensional analysis? You know, could we have figured out like how much O2 you need to react with the so I might have said this question here as a second approach. Or maybe even the first approach, like once you see the BCA chart, it makes sense. Usually we're running to dimensional analysis. Like if you come to my office hours in the next week or two to talk about stoichiometry, I'm almost always just going dimensional analysis. But it's one of those things, like if you don't get the BCA chart, a lot of dimensional analysis we're gonna have issues with. But once the BCA chart makes sense, I think you can make easy sense of, well, the number of grams of O2 that are required to have reacted to produce the 76 grams of water can just be solved off the stoichiometry reactions, just the grams to moles. For every 2 moles of water that formed, we needed 1 mole of O2 according to the balance reaction to have reacted. So the 2 to 1, this is just coming off the coefficients in the reaction. And 1 mole of O2 is 32 grams. So if we'd just gone 76, divide by 18.02, divide by 2, times 32.00, there's our 67.5 right off the bat. And again, we're pretty much locked into A because none of the other choices had 67.5 grams. One of them's close, like answer D is pretty close. So again, we might want to double check if this is a test to make sure we didn't have a rounding error. But That's a lot less work and thinking than the BCA chart, right? But the key is that it may not have made any sense if we don't understand what the BCA chart is showing us, just the relative way that these reactions are working, that we're losing reactants, gaining products, etc. Could I have found out how much hydrogen reacted off one-dimensional analysis step? Yes. Can I figure out how much hydrogen remained off a single calculation? No. So we got to think hydrogen that had reacted with to produce the amount of water. I can do that by dimensional analysis. Then I have to do a subtraction step, like a two-step process, to get the amount of hydrogen that remains. So I may have thought of this again. Let me just go this way. The number of grams of H2 that reacts to produce the 76.0 grams of water we can solve using dimensional analysis 2, 18.02 grams per mole of water. It's 2 to 2 for every 2 moles of water that were formed. 2 moles of H2 had to be consumed. And again, the 2 to 2 is just off the coefficients in the reaction. So just the 2H2, 2 water. And then 1 mole of H2, 2.016 grams. So 76 divided by 18.02 times 2 divided by 2 times 2.016 is 8.50. Or yeah, 8.50. And if I take the initial amount, there was 12 grams of hydrogen given. Maybe if I included an extra sig fig, I lost the extra sig fig somewhere along the way here from the 3.49 to the 3.50. But, I'm getting 3.49, 3.50 grams out for my H2 that remain in the reaction. I just start with the initial, minus the amount that reacted, and I get the amount that remains. So, BCA chart useful for thinking, I think, and helping us understand what we're doing in the dimensional analysis. But I think you can see that the dimensional analysis took me like 2 seconds to set up and write out. I probably could have done that once, especially we get through a few practice problems and you do homework tonight, do a few review problems. I mean, you'll be doing the conversions hopefully in your head and accurately in your head without writing necessarily everything down. So the conversion problems in stoichiometry usually pretty straightforward, but we just have to be thinking along the way and have very good minds, be very mindful of the steps that we're doing, and then it all comes together pretty easily. Okay, so we then kind of come back to a particle diagram. We started particle diagram, and we'll end with a particle diagram for the coverage of chapter 3. And we see a box here that has 6 chlorines, 6 fluorines. We have 6 F2s and 6 Cl2s. And so these molecules are reacting to form chlorine trifluoride, which of course would be ClF3. But what we might have to think is, well, what would that balanced reaction look like? So if I'm taking Cl2 as my chlorine, my F2, reacting that together to form ClF3, then we have to take, a 2 in front of the ClF3 to have 2 chlorines on both sides. That's 6 fluorines on both sides, so I'll have a 3 F2. So 1 Cl2 plus 3 F2s give me 2 ClF3s. And so maybe we had to think about how this would balance out. So we had to think, okay, we probably should write the balanced reaction. If we have a stoichiometry problem, we should make sure to balance out the reaction. That'll help us see that if I take, now there's 6 of each, so it doesn't really matter which one's which, but let's call this one the chlorine, and then this one the F2. And so then we'll take a chlorine and 3 F2s, react them together. If we're drawing that, it might look like this. And then again, for my other ClF2. And now I might think about putting them not necessarily, like they're going to be in random locations in the container is what we're trying to show. So it's just a homogeneous container. So they're going to randomly be somewhere inside the container. And then we can do this just one more time. So we do it one more time and we get another ClF3 and another ClF3. And then what are we left behind with? 1, 2, 3, 4 F2s. So once the reaction completes, we have the products that form. So in the reaction mixture or in the container or the system that we have the products that have formed and then whatever's left over. So then we are left behind with whatever excess reactant that we had. And so we have 2 molecules of, we have 4 fluorines that remain. All the chlorine has been consumed when that reaction completes. And we form 4 molecules of ClF3. Okay, so we can still think through a particle diagram when those kind of problems come up. So you'll see some particle diagram representation problems that just require us to think about what's going on, or that we can think about what's going on from a pictorial perspective. You could also go back, I'm not going to go through the math, but you can go back and say how many molecules of F2 react with the chlorine, how many Cl2s react with the F2s. You can write this out dimensional analysis, you can set up BCA charts, or in this case, sketch a picture. Okay, so I actually, circled the wrong one. It's the chlorine that's left over. So we have 4 chlorines left over, and all of the fluorine has been consumed. Review packet, it's a couple of questions from chapter 3. I don't know if anybody's seen this, but in the lecture slides area, there's a review, chapter 3 review. The very last page is a set of questions we'll do today. And then throughout the chapter 4 notes, we'll look at some of those other questions from chapter 3 to review stoichiometry once we get removed from today's lecture. So let's look at the first question here. These are just old quiz questions or exam questions from the past. So a compound with a molecular weight 4 times its empirical formula mass has a composition 88.8% carbon, 11.2% by mass for hydrogen. What's the molecular formula for this compound? Now, a few ways we could go, but the key is empirical formula. I can get the empirical formula from the percent mass data, and then I need 4 of those units in the molecular formula. So my thought is get the empirical formula, and then just 4 of those for the actual molecular formula. Okay, so my empirical formula, I'm going to take the 88.8% by mass carbon, so it'd be 88 grams of carbon that are present in ratio to 11.2 grams of hydrogen. So I have a mass ratio for that compound of carbon to hydrogen. I just need to go to a mole ratio. So I just need to use the molar mass of carbon, the molar mass of hydrogen, and since it's mole of H, so we use the molar mass of H. Previous problems today had H2. That's why we're using the molar mass of H2. Sometimes we get caught up early on of just when do you use H versus H2. It's just whatever you have here, use the molar mass of that thing. Okay, so if we calculate the moles, again, it's the ratio of the moles in this sample that we're starting with, where we know the mass ratios have to be true to be reflective of those percent masses. So I get 7.39 moles of carbon in ratio. So it's going to be about 11, but 11.2 divided by 1.008 is 11.1. Then if I do any math to either one of them, I got to do the same math to the other. So if I divide one by a number, I have to divide the other by the same number. So one approach here is just to find the smaller of the two, which is 7.39, and divide both of them by that number to keep the ratio intact. So of course we get 1 mole of carbon present in ratio to 11.1 divided by 7.39, which is 1.50. Then I just think multiples. If I don't get whole numbers, I need to be within, I think pretty clearly, so I'm going to double here, but I need to be within 0.05, and it's usually going to be very, very close when you can round. Like you got to be really close to a whole number to round is what I'm saying. And so of course 1.5, nowhere near a whole number. So I need to start thinking, do I double these, triple, quadruple, and I start smallest, so I go times 2. Do I get whole numbers? And of course I do. So if I go times 2 to both of these, I get 2 moles of carbon in ratio to 3 moles of hydrogen. So the empirical formula would be C2H3. And then the formula has 4 of those units. So just times 4 on both of those. So it'd be C8H12. Question 2. A compound is known to have a formula XCl3. So for every X, there's 3 chlorines in this compound. If the compound is known to contain 79.8% by mass chlorine, what's the atomic weight and identity of X? I think this is a tricky problem because, I don't know if we've seen anything quite like this, but we do know what percent by mass means. Like when I say, what does the percent chlorine mean? Well, it would mean for this molecule, since there's 3 chlorines, it'd be 3 times the atomic weight of chlorine from the periodic table. Divide by the formula weight of that compound or that molecule that we don't know because we don't know what X is. So, but 3 times 35.45 divided by the formula weight times 100% is what the percent chlorine means. And we know that that's 79.8% by mass chlorine. So do you see how we can solve for the formula weight? Because it's the only unknown in this equation. So I can solve for my formula weight. Let's get rid of the percentage. So let's write 0.798. Get rid of the percentage. So just have the fraction. And so then my formula weight cross-multiplied over to here. And then divide both sides by 0.798 to cancel that out here. So we're just algebraically solving for the formula weight. So if I take 3 times the chlorine mass in the periodic table, divide by 0.798, the fraction that's chlorine, the atomic weight, the formula weight of the compound would be 133.3 AMUs. Which is, of course, the atomic weight of X plus the 3 chlorines. So let's just subtract off the mass of the 3 chlorines from the formula weight. So 133.3 minus 35.45 times 3. Oops, calculated wrong. 133.3 minus 3 times 35.45. I get 26, call it 27.0. So X has a mass of 26, okay, I got 26.95. Maybe I could have called it 26.9, but about 26.9 to 27.0, that's the atomic weight of aluminum. And if you want to double check, if you just did the 3 times 35.45 plus 26.9, that's the formula weight, and then solve for the percent chlorine, 3 times 35.45, then we get the percent by mass chlorine. Like you can double check. Okay, so we're just using what a percent mass means in that second question to solve for the formula weight to then be able to determine what the atomic weight is for X. And then how many O atoms are present within a certain mass sample? How many, like number-wise, you can see, should be a big number or a small number. Like if you had how many O atoms in total are present within a 6.5 gram sample of CO2. There's going to be a lot of O atoms within that sample, right? So the way we would solve for the number of O atoms here is to go from 6.5 grams, let's be precise, 6.50 grams of CO2. The molar mass, we go grams to moles, moles to molecules, and then inspect the formula to get the O count is our process here. So it's 44.01 grams per mole of CO2. Just 12 plus 16 times 2. For every 1 mole of CO2, that would be an Avogadro's number of CO2 molecules. every molecule of CO2 has 2 O atoms within it. So I'm just inspecting the formula, 2 O atoms per molecule of CO2. So I go 6.5, divide by 44.01, times Avogadro's number. And that's 2 O atoms, not 20, making sure you don't see it's 20. But then times 2 gives me 1.78 times 10 to the 23. For answer B. Okay, so just a couple of review problems to take us back to early chapter 3. Let's jump ahead here. Let's wrap up with our lecture quiz. And so once you mark your attendance, keyword today is ionic. You're free to leave after that. So thank you guys. Have a great day. And wrap up